In this lecture, I'm going to give you an overview of the DeepSpec project, what we're trying to accomplish, what we have accomplished, what we hope still to accomplish. DeepSpec is a 5-year expedition in computing funded by the National Science Foundation. It's also a consortium of different research projects at 4 universities on the east coast of the United States, all doing program and hardware verification research in Coq. So when you think about verifying a program, what does that mean? You could run a verification tool on it. And some kinds of verification tools work fairly automatically on shallow specifications. For example, the type checker of your ML compiler or the type checker of your Java compiler is a kind of program verification tool that, because the type systems of those languages are sound, if the program type checks, then in principle it is not subject to certain kinds of bugs, like array subscript out of bounds, dereferencing uninitialized pointers, and so on. And therefore those programs are generally immune to some kinds of vulnerabilities such as buffer overruns. And that's good because type checkers are pretty easy to use. They don't require a lot of effort by the programmer to verify the program. And there are static analysis tools that you can apply to your program that also work fairly automatically or with a small amount of programmer inserted annotations and assertions. But when you verify programs without specifications, you can't verify that the programs work correctly. You can only guarantee certain generic safety properties about the program. That is, as J.J. Horning said decades ago, a program without a specification cannot be incorrect. It can only be surprising. Because what it means for a program to be correct is that it satisfies its specification. It does the thing you wanted it to do. And unless the only demand you have of a program is that it doesn't crash, then you need specifications. So these static analysis tools and type checkers are very useful, and it would be a good thing for the world if they were used more often on more kinds of programs. But what we're interested in DeepSpec is correctness verification. We want to verify that programs do what they're supposed to do. So we want to do research in how to specify as well as how to verify programs. Components such as operating systems, type checkers, static analyzers, compilers, runtime systems, garbage collectors, cryptographic protocols, the things that form the infrastructure of our computing world. And our scientific hypothesis in DeepSpec is that we want to study rich, formal, two-sided, and live specifications. I'll define all these terms in just a minute, and we call those deep specifications, as opposed to the shallow specifications that are just about generic safety properties. And we hope that this research will lead to major advances in the reliability, safety, security, and cost effectiveness of software and hardware. So, what do we mean by rich specifications? Ones that describe complex behaviors in detail. That is, for example, describe functional correctness properties that the program that accomplishes a particular thing rather than just a basic safety property that it won't crash. Formal means in a notation with a clear semantics. That is, for example, logic. And formal also means in a machine representable logic that you can check properties of with tools for logic, such as, for example, Coq. Two-sided. When you verify that a program module satisfies a specification, what if the specification is wrong? But when you verify that some client of the module it can be proved correct with respect to that same specification, then you have more assurance that you've specified something useful to the client and achievable by the implementation. And by connecting different large pieces together, we can make two-sided specifications at their interface and gain confidence in them. And finally, live. We want to prove the properties of real programs, not just algorithms or functional models of the programs. There's been a lot of really good verification work in previous decades where you write down a functional model of what you think your program is doing. You prove that the functional model has the right properties, but you don't connect it to the actual implementation, the real source code of your real program. And so in DeepSpec, we also want to work on tools that can connect your functional model to the real implementation. And that's what we mean by live, machine-checked connection to implementations. We're going to do all of this work in Coq, partly for the two-sided reason. We want to connect the verification of one component to the verification of another component at interfaces. And since many bugs can occur at the connection between different modules because of different understandings of the same mostly formal specification, we want to do the connection seamlessly and end-to-end in the same proof assistant. And for that, we've chosen Coq. So Coq has several components. There's a logic, the calculus of inductive constructions, in which you can write down specifications, theorems, proofs, and even functional programs. The kernel of Coq is a proof checker for proofs and terms in this logic. Coq also has a proof assistant outside the kernel that helps the user build such proofs, checkable by the kernel. It has a programming language called LTAC for programming scripts that will build proofs that are checkable by the kernel. It has libraries of theories, that is, definitions and theorems about those definitions that you can use in the definitions and proofs about a particular program. For example, the theory of integer arithmetic. It's really useful to be able to compute with integers. And so the Coq library has definitions of the integers, operations on the integers, and then commutativity and associativity properties of those operations, and so on. But the libraries are much more comprehensive than just the integers. Coq has a big user community, and it's well supported by the development team at INRIA in France. So, what does a proof in Coq look like? I think all of you in this room knows what a proof in Coq looks like. You have on the left your proof script. First, a statement of some theorem, then the commands in the LTAC language, which claim to be a proof, claim to build a proof of that theorem. The green part on the left is the part that in this session has so far been accepted and type-checked by the proof assistant. And on the right, we have the current proof goal, what remains to be proved, which looks like it should be proved by that proof script on the left, yet to be checked. So the user writes the things on the left, the statements of the theorems and the proofs, and the proof scripts, and the Coq kernel checks that the proof scripts are building valid proofs of those theorems. Okay, so if you think about the proof of correctness of a compiler, let's say an optimizing C compiler that translates a C program to a machine language program, that proof of correctness will be with respect to an operational semantic specification of what C programs do, and with respect to an operational semantic specification of what machine language programs do on a particular machine. And if you think about the verification of a web server is implementing the HTTP protocol, so at the top we'll have the specification of HTTP, and the web server is written as a C program, So in some sense, it's a client of the semantics of the C language. So there are some big specifications in there. The specification of the C language is a big thing. The specification of HTTP is pretty big. The specification of your machine is big. And when you write programs, you can have bugs, but just as much when you write specifications, you can have bugs in the specifications. And so proving a program correct, but to the wrong specification, can lead to just as many problems as an incorrect program. Now, the point is that when you connect big components end to end, the bugs in the specifications of the connecting specifications between modules tend to be less important. They drop out. Suppose the web server is written and executes in a language which isn't quite C. It's somebody's idiosyncratic interpretation of the C standard. But the compiler is proved correct with respect to the translation of that idiosyncratic interpretation of the C standard. Then whatever properties you prove about the behavior of the program will still hold with respect to the top level, which is the specification of HTTP, and the bottom level, which is what happens when the transistors fire. So these internal specifications, even quite large ones like C and machine language, are two-sided. And the ratio of the size of the specification to the size of the implementation will decrease as you verify larger and larger connected collections of components. The DeepSpec team has many different individual large projects, and I'll talk about each of these projects. And each of these projects is interesting in its own right, even if we're not connected to many of the other projects. But the goal of DeepSpec is to connect these projects together at specification interfaces to make a whole that is more than the sum of its parts. Okay, so let me talk about some of the individual projects. The Verified Software Toolchain is a project at Princeton it's a tool set for verifying the functional correctness of C programs. So you operate it within the Coq Proof Assistant. It applies with proof automation tools a program logic to the C program. And the program logic itself is proved sound with a machine checked proof in Coq with respect to the operational semantics of CompCert C, and that connects to the proof of correctness of CompCert itself done at INRIA. And some of the demonstration projects that we're doing, have done, and continue to be doing for the Verified Software Toolchain are cryptographic primitives, such as the secure hash algorithm, the HMAC cryptographic authentication system, the HMAC DRBG random number generator, a mailbox communication system, a garbage collector, a database management system using B+ trees, and a web server. Certicos is an operating system verification project that's been going on at Yale University for several years. Certicos is the Certified Kit Operating System, and there are really two kinds of research going on here. One is the proof methodology. It's an alternate methodology for proving the correctness of C programs, certified abstraction layers, in which you prove by refinement that C programs implement functional specifications written as pure functions in Galena. And then this certified abstraction layers methodology is applied to the verification of a pretty high performance, capable hypervisor operating system kernel, which runs on several real platforms. It can boot Linux, it can run guest operating systems, even in multi-core mode. It has quite a few verified device drivers, and so on. Vellum is a formal specification in Coq of the widely used LLVM intermediate language and compiler infrastructure. So LLVM is the basis of the Clang compiler for C and C++, but also for many other source languages which target LLVM. It's an intermediate language based on static single assignment form. Vellum is implemented in C++, LLVM is implemented in C++, and Vellum is a formal model of it, a version that's implemented in Coq, compatible with the C++ version. And the formal specification of the semantics of the intermediate language is then used in proofs of correctness of examples of LLVM compiler phrases. And so for demonstration projects, it's going to be used as the basis for testing the correctness of GHC, the Glasgow Haskell compiler that targets LLVM, perhaps using the quick check tool that I'll also describe. The Haskell core spec is another deep spec project that is a formal semantics in Coq for the Haskell core language. If verifying functional programs is a good idea, you might want to verify your Haskell programs, but for that you need a formal semantics of the Haskell language. So this provides a formal semantics, and then it allows to prove the correctness of some of the GHC phases, right, as transformations on this formal semantics. Another part of this project is the HS to Coq tool. It's a translator from Haskell into Coq. So you take your pure functional program in Haskell, you translate it into a pure functional program in Galena, the functional language inside Coq, not for the purpose of executing it. GHC executes it quite well, but for the purpose of proving things about it. The proofs you do about the HS to Coq translation of your Haskell program can serve as verifications of the correctness of your Haskell programs. And this, we're using then the Coq logic to prove things that almost directly about Haskell programs. Certicoq is a verified compiler for Coq programs. One of the really nice things about Coq is that you can write a functional program in Coq, verify it using Coq's logic, then use Coq's extraction facility to print out an ML or a Haskell program, and compile that with OCaml or with GHC. But the extractor tool in Coq is just a plugin written in OCaml. It's not proved correct. And the OCaml compiler or the GHC compiler are not proved correct. So Certicoq is a combined extractor compiler that compiles Galena programs through C, targeting CompCert to get all the way to assembly language for various target machines, and where the entire chain is proved correct.
What is the status of that?
What's the status of Certicoq? It works. We haven't done the public release yet. Almost all the phases, the verification of correctness has been done. There's one or two phases where the verification of correctness is still in progress. And to use a technical term, we expect to do a release real soon now.
And open source?
And it is open source. Kami is a project to do verified processor design and, in general, verified circuit design using a pure functional paradigm. It's based on the BlueSpec language developed a few years ago by Professor Arvind at MIT, but Kami is a way of doing Coq proofs of the correctness of BlueSpec designs. And then, so you prove, you write your processor design as a collection of functions in Coq. You prove that that collection of functions implements the behavior that you want, and then the Kami system can also compile it down to VHDL. And then in the hardware verification community over the past 20 years, they've developed pretty good tools. How do you do hardware design in the real world? You write An RTL